John Dalton's theory. Remember the 4 things we talked about? Okay. Oh, good. We're getting more. Woohoo! Anything else, or was that? All right.
Nice.
Oh, thank you. Yeah, it was dress up day today.
And I missed it.
Okay, I gave you a periodic table with 2 periodic tables on one sheet so that you can take notes. We're going to do that today. Sorry, we didn't get to it last time. So first thing we're going to talk about, unless we have any questions. Are we good then?
Asking questions about the are we going over review questions?
Not yet. No, we're going to go over the periodic table. We're going to finish up that today, and then we'll have time for questions, hopefully. I mean, if you want to stay later, we can keep going, because I'm here till 4:30. So, I mean, I have a class from 2 to 4:30, so, but, yeah. You're welcome to stay as long as you need. We good then? All right. So the first part we want to talk about on the periodic table, so last time we talked about periods and groups, right? Periods are the rows, represent what? The energy level. Good. And we'll talk a little bit about that today, but we keep it at a minimal. This class is supposed to be pretty straightforward, not too deep. If you want to take a deeper course, you take 1210, right? And then what? And then the groups. What do we know about the groups?
It's the same element, close to each other.
Similar properties, right? If the elements are in the same group, they have similar properties.
What kind of similar, for instance?
Well, we talked about a few, right?
Yeah.
So those things we burned, right?
Oh, yes.
Bright things, that was in group 2. We threw a few in water. That was group 1. What did they do in water?
They
Caught on
also-
fire, right? Or they reacted.
Right.
Some of them didn't catch on fire, but if we had more of it,
It's
right?
because the sodium losing one electron to the
That's
water
right.
molecule. and
That's
then
right.
it's heavy reactive happen.
Yep. Well, that's why it's reactive, because it loses it pretty easily. It would say, hey, give it, and we'll talk about that next unit a lot more. Okay?
So this group 2, everything is the same reactive to the water.
Not the same reactive, similar. Do you get the difference?
Yeah, similar.
So same means equal,
Oh, similar,
and
close
similar
to
is
each other.
close. Not exactly, but similarly, right? Kind of the same, right? Question?
I was going to say aluminum and copper are like that. They're both
Yeah.
e-dissipation of both of them.
Yeah. Copper, silver, gold, they're all in the same group. Great conductors, shiny. Yeah. They're kind of similar, not the same. All right. Any other questions? Okay, so classifications of elements. There's 3 classes of elements, just 3. I'm going to show you the one that separates the 2 so that it'll be easier to know which is which, okay? So, all right, let's do, so if we start at boron, number 5, and we draw a staircase that goes down to tellurium, and actually it goes clear down to polonium, and then it includes antimony, germanium, not aluminum. All right, so those elements right there, not very many. So it's the staircase. So if you think about, here's our original staircase. This line here, direct straight line. And then you go down one and you do three more. You can remember this. This will help you to know all of the other elements, the classes anyway. Good? I'm going to erase those lines. All right, so we're going to call these the metalloids. And we'll talk about properties in just a minute. Yeah, Eric.
I'm colorblind, I'm having a hard time seeing color. Can you tell me which numbers or anything?
Oh, my bad. Should I? Let's see. Yeah, so we start at number 5, boron, and it goes in a diagonal, silicon number 14, arsenic number 33, tellurium number 52. And then you go straight down, and we include polonium number 84, antimony number 51, and then germanium number 32. So we go diagonal, down, and diagonal back up, but we don't include aluminum. I hope we all know aluminum is a what? Metal, right? So these are the metalloids, and these separate the metals from the nonmetals. So now, next, let's do the metals. And the metals are everything to the left except for hydrogen. So hydrogen's number 1, everything to the left. And what about these bottom ones? Where do they go? They go right there, right? So they're also to the left, even though they look like they're to the bottom. You with me? So it includes aluminum, tin, bismuth, and I'm just going to cover all this. Those are the metals. So most elements on the periodic table are metals. And then the remainder of them we call nonmetals. That includes hydrogen and everything to the right of the metalloid staircase.
They are metal.
What?
They are metal.
Metal? Yeah, yep, yes. So the metals are the red. Well, everything to the left of the staircase. Any questions how to tell what class of element the elements are?
So this one go to the lithium, you go carat or no?
Right here?
Yeah.
No, that's just where these go right here. These metals down at the bottom. If you look at their numbers, so this is 57 and this is 72. You see that? Where's the rest of them? Down here at the bottom. 58 to 71. Same thing with 89 to 104. You got 90 to 103. So they just kind of fit right in the middle of those guys.
What's
Yeah.
boron?
Our textbook has a few things a little differently. Should we go off of this chart?
Are you talking about the metalloids?
Yeah.
Yeah.
It has-
And every periodic table will be slightly different. But fortunately, if we have a bracket for the atomic number, that tells us it's not very well. It's not abundant. It's not very stable. It's kind of I mean, the properties it has in this general conditions or environment, they don't exist.
Right, because it's always.
So we don't talk about those a lot,
Okay.
so we'll be okay.
Okay.
Great question. But yeah, anything, bring it up, please. Are we good there? Yeah, Chad.
What are the green circles? Sorry.
Oh, I just showed that that's where these bottom elements kind of go in between. I just circled the numbers to kind of show you, but have nothing to do with the classes. Thanks for asking. Anything else?
Mentally, how do you take mentally, what does it mean?
Well, let's talk about what they are. Okay, so metals. Metals are, I think we're all familiar with metals, right? Maybe not all of them, but okay. We know metals are mostly solid, right? There's only one that's not solid, and that is mercury. Okay, so they're solid. They're shiny, or they got a luster surface. Most of the time, when we look at metals, that's what we think of, right? They are conductive. They are malleable. What does that mean?
You can have them molded into shape.
Yeah, you can shape them, right?
Shattering.
Yeah, so they're not brittle. You can shape them. Some are soft, some are hard, but we saw a few soft ones yesterday or last time. And then they are ductile, means you can make wire out of it, which is kind of a property of malleability. So those are metals. Good? We okay? We understand metals? And nonmetals are kind of the opposite of that. They're not good conductors. We'd say they're good insulators, right? They don't allow heat or electricity to flow through them very well. They are brittle. You smash it with a hammer, it'll just break apart. You guys, so carbon. Do you know anything made of carbon? Coal. And if you speak Spanish, what's coal in Spanish? Carbón. Spells like carbon, right? So that's what it is. So coal, you smash coal up, we hit coal with a hammer, what happens? It just breaks. It's brittle, okay? Are all nonmetals brittle? No, there's a lot of gases too, right? Some are gases, so is it always going to be solid or gas? It could be liquids too. So it's kind of all over the board there. So that's nonmetals, a lot of gases. And then metalloids. What kind of properties do metalloids have, do you think? Somewhere in between. Oh, that's nice, because that's where they're located on the periodic table. They're somewhere between the properties of metals and nonmetals. So that you might, for conductance, they're semiconductors, right? Somewhere in between. They're probably not hard or brittle. They're probably somewhere in between, okay? Does that make sense? All right. Any other questions on the three classes of elements? What? Metalloids? Well, let's see. So silicon. Silicon, I mean, you go to Home Depot and get some silicone, right? But it's probably a compound with silicon in it. And so what is that? It's kind of not hard, it's not brittle, it's rubbery-ish, right? And is that exactly silicon? Probably not, okay? It's a compound of silicon. But, and again, let's see, let's look at some more that might be. Arsenic, you've heard of arsenic before? Yeah, they're just somewhere in the middle. I don't know how better to say that. We good?
Why you circle 1958, 71, 1 and 2?
Because I was trying to explain to you where those go. Why I put this line here.
small circle.
Yeah, because 57, 72, 58, 71, you see how they fit in between? That's all. Has nothing to do with classes. Are we good? All right.
Sorry, I didn't catch why you circled the red circle. for
Yes, the
loading.
red circle, I was asking this.
Oh, right here?
Yeah, what was that?
Okay.
Explain.
So we talked about the metalloids might be different elements on a different periodic table because whoever wrote it, what is it really? I don't know. So, but we looked at the brackets tells us they're not really abundant and we don't use them a whole lot anyway, so it'll be fine. Good?
There's one more question.
Any other questions? Yeah, Eric.
Is everything higher than lead radioactive?
Well, you mean lower
Or
on the
like
periodic table,
higher
bigger number? Anything bigger than bismuth. So you see all these brackets after that? Not all of them, but most of them? Yes.
And the bracket means that it's radioactive,
Kind of-ish, not exactly.
or that it has a half-life or something?
It's not stable or it doesn't exist in the conditions that we live in.
You have to create it in lab,
Yeah. Uh-huh.
like maybe this one that has nibellium, it has high radioactive item.
Yes.
For
Well-
1 or 2 protein.
Maybe. I don't know
It's
for sure.
created in lab, nibellium?
If it's in brackets, probably, yeah. And there's actually, this is an old periodic table. These are actually other elements that have been discovered or formed in a lab with specific conditions. Okay? We good? I love these questions.
In the future, it will get in more.
We're not going to go that deep, guys. You guys are going way too deep.
They will keep creating still.
Yeah, maybe this is just a drop in the bucket. I don't know. Yeah, we don't know that much science. I mean, we don't know that much compared to what there is to know, is what I'm saying, right? Yeah, Sterling.
So in the textbook, it says that there's another element with the atomic number of 112. It's copper and nickel,
Uh-huh.
CN. Should we know that?
No.
Okay,
No. If it's not on here, you don't need to know it.
okay.
Probably not even for a higher class. It's, yeah. So once you know this pattern or this periodic table trends, we'll talk about some trends today, then you can kind of predict other elements. And that's kind of how, when we first come up with a periodic table, Mendeleev come up with it, he predicted gallium. He predicted the properties of gallium and everything, and he got it right. I don't think he discovered it, or he found out about it, but he predicted what the properties would be based off of this periodic table. So pretty cool. And we can continue to find more elements, I'm sure. Are we good? Great questions. All right, let's move on to groups, the different groups on the periodic table. So I'm going to pull up another one. And, yeah. And if anybody needs an extra periodic table to take notes on, I have some more. And anyway, just let me know. All right, so the different groups on the periodic table. The first group, and we kind of talked about some of these yesterday, but we didn't give you the name really. So, group 1, not including hydrogen. Why is hydrogen even there?
It's because of one protein.
Because it's the king of exceptions, right?
Excuse me, can I get another periodic?
Yeah. Anybody else need one? All right. So this first group, we call these the alkali metals. And just like we saw last time, these are the most reactive metals on the periodic table. Okay. And then so that's the first group, if you can't see the color. So 3 to 87 in that same column. And then the next group over, group 2, these are the alkaline earth. So the alkaline batteries, the ones that when I lit on fire, bright light come out, yeah? So these are the alkaline earth. Metals. And then let's do group 17 on the periodic table. These are the halogens. And halogens are the most reactive nonmetals. And we'll talk about why that is, why these two groups of elements are the most reactive. And then group 18, all the way to the right of the periodic table, these are called the noble gases. Often these are called inert gases. What does inert mean? Yeah, okay. It comes from a physics word, inertia. What does inertia mean? The tendency to resist change, right? And so that's exactly what noble gases do. They don't want to change, so they don't react with anything. These are the least reactive elements. And that's why, well, is it okay to breathe in helium? Is it bad for us? Does it kill brain cells? If you don't breathe oxygen in between, right? So that's the only reason why it's bad for us, because it doesn't react with anything in our bodies. But our bodies need oxygen to live, right? So anyway, that's the only reason. So people say, it's going to kill your brain cells. Yeah, if that's all you breathe. Just like if you quit breathing, you're going to go brain dead, right? Okay. I'm not saying go ahead and breathe off. My teacher said. Right, okay. All right. And then 2 more groups. I'll just do this. I'll just write it right here. These are called the transition metals. Can you see that? Okay, Eric. So the guys in the middle, group 3 to 12, these are the transition metals. And why do we call them transition?
I already said to ask.
Yeah,
Does that
or
include the
Chad,
bottom
sorry.
two rows?
No. Nope. Good question. So the reason we call these transition metals, and there's really no logic, I mean, I guess it is logic, but there's no other reason than, well, let me just tell you. So right here, the first 2 groups and the last 6 groups, these are called the main group elements. Why do we call these the main group elements? We know more about them. Okay? Main group elements.
Which one's that?
The ones, so the first 2 columns and the last 6 columns. Okay. And transition metals, well, and I'm going to draw something on here. It's not going to mean anything other than so that you can see what I'm saying. Okay. So it goes from main group elements to main group elements. It transitions from main group to main group. That's the only reason we call it transition. Okay. So it's just a name. And then down here on the bottom, well, where are these located? In the transition metal. So we call these the inner transition metals. Sometimes you might hear these as the rare earth metals, but they're not necessarily rare, and so we're just going to call them inner transition metals. Are we okay with those names? Question?
What's the bottom one called again?
Inner transition metals, because they are located inside the transition metals. Any questions? Yeah, Erica.
Groups 13, 14, and 15 have a specific,
Name?
yeah, classification.
Um,
That we need to know.
No, we don't need to know it. There's these guys right here are the chalcogens, but only those 3. It's like, why? Because these ones are metalloids. They're a little bit different, right? So we're not going to group those together. And right here, these are the, can't even pronounce these ones. Nalcogen? I can't remember. But we never use them. I never do. We don't use it in this class. So, but yeah, we don't need to worry about that.
Which one the most we are worried about it?
All of them. Get them all down. Because I might say, which of the following elements is a transition metal? And you got to know where they are. Oh, and you just look at which ones belong in this group, right? Which of the following elements is a metalloid? Okay, which is on the staircase? You with me? Or which of the following is a noble gas, and so on. Make sense? So you really need to know all of them so that you can differentiate them. Any other questions? All right, let's move on to electron configuration, where the electrons are located in an atom. So remember we talked about Bohr's model. I think we talked about Bohr's model. Okay. So Bohr's model looks something like this. Is the color better on the black screen? Okay. So here's Bohr's model of the atom. But that's not really how they look. And I'm going to use this a lot because it's easier to explain things. Okay? But how they really look is, let's think about can you guys tell what that looks like? It's not chemistry, I promise. Oh, okay. This is why I'm not an art teacher. And if you would have guessed right, I'd say, maybe I should get a minor in. No. No, this is like a fan blade or something, right? So that's what a fan blade, we can know where that fan blade is. It's right there, or it's right there, it's right there. You with me? And, okay, but now let's turn it on. And it'll look something like this, right? Kind of like a big blur. Or is a fan blade? It's somewhere in that region. So that's where that's kind of how electrons are. They're not just hanging out on these specific levels, specific rings. They're not just, it's not how it works, okay? But in reality, they are, so we have a few different types, and I'm not going to really go deep into this topic, guys. I'm not. Yeah, so let's start with, if that's the nucleus, then where's the electron? Somewhere in that region of space. Does that mean it can't be right there on the outside? No. But the highest probability of where that electron is going to be is somewhere in that region. For smaller atoms, that's where it is, right? Or for the electrons that's closest to the nucleus. And then if we go out a little bit, then it's going to be somewhere in these regions. And I'm drawing this to kind of look like it's 3D, where you got one on the x-axis, one on the y-axis, and one on the z-axis. Can you see that? So there's Z, there's the Y, there's the X. No? Yes. Okay. So the electrons are somewhere in those regions. That's the highest probability you'll find the electrons. And that's all I know how to draw. They get funky, and you can look them up. We won't have to worry about it for this class. But they look a little bit different than Bohr's model. But he said they have specific energy levels. And that part is still true. But, so, Bohr says an electron couldn't be right there. But it actually could. It could have, if it's out further, that means it's going to have more potential energy, right? But what if it's going faster? Or slower, right? So if it's closer to the nucleus, it's going to be going faster because there's more traction. You follow? If it's further out, it's going to be going slower. So here, it has less kinetic energy and more potential energy. Right here, it has more kinetic energy, less potential energy. But together, all of their energies is equal to the same thing. So that was straightforward. That was dead on, the Bohr said. Are we good there?
What is that?
What?
You said it's electronegativity.
We'll talk about electronegativity in a little bit. Not yet. Okay? Any other questions? All right, let's go back to Bohr's model because it's easier to understand. Okay? And let's did we talk about valence electrons yet? Okay, let's do that. Let's do that next. And so you can use one of your other periodic tables that you labeled, and I'll just get a new one. All right, so, and does red work on here? Does red work okay, Eric? On the white? Or shall I use black?
Black is better, I don't see any color red.
All right. So valence electrons are the electrons on the outside of the atom. Valence means the outside, I guess. Okay, so valence electrons, and these are the only electrons that participate in a chemical reaction. Only ones that change. So really, these are the only ones we're interested in. okay, for this class anyway. Valence electrons. These are the electrons in outermost energy level. All right, now I'm going to come back to this in a minute. I'm going to draw Bohr's model for some of the atoms. So let's do, so for hydrogen, we have the nucleus. How many electrons do we have for a neutral atom? 1. Did we talk about this? Okay, my bad. My 1210, we're kind of little. We go a little bit deeper. Okay, so we have 1 electron. So it looks like this. You follow? And then if we go to helium, which is all on the other side of the periodic table, or this side of the periodic table, then we have 2 electrons. And that's all that can fit on that first energy level. Why? Because they're so close together, and electrons, what do they do when they get close? They repel. That's why I draw them exact opposite sides, furthest away they can be, right? Question?
Is that because they're both negative and so they?
That's right. Yep. Like charges repel, kind of like we showed with that broken tape last time, right? Okay.
How they get their charge to active levels?
How do what?
How they get their charge energy to?
How do we get the chart? What?
No, how the electron get the energy or charge that's moving?
Great question. Great question. Look that up. I bet it's physics. How did it get it?
No, what do you think? It's just something theoretical, we don't know.
It's moving. It's always moving, and it's moving almost the speed of light fast.
Yes.
So how did it get it? I have no idea. It was born with it, I guess. Yet it's not born. So, yeah, I have no idea. All right. Sorry, I'm sorry I don't know everything.
No, that's okay. I thought maybe you have an answer, but even the physics doesn't have answer yet.
Yeah. All right, and maybe there is an answer. I just don't know what it is, right? Yeah, you can look it up. Ask ChatGPT. Maybe it knows, right? Okay. So then let's go to lithium. Lithium is right under hydrogen, right? So if we draw, and I'm going to try to draw this a little bit smaller. This time we have 2 energy levels. Any ideas why we have 2 energy levels? First one is full. Yeah. First one is full. So we have to go out to the next energy level, right?
Which is 8.
Can we see that on the periodic table? Here's energy level 1, 2, 3, 4, 5, 6, 7. So lithium is in energy level 2. But not all electrons of lithium are on energy level 2. The first 2 are on energy level 1. First, so we can kind of look at this as the electron table for a minute, right? And these are all in number order, yeah.
So the energy level says like how many circles are on the other.
That's right. Yep. Okay. And if we go over to neon, right here. So neon is also going to have how many energy levels? 2. It's on row 2. You with me? How many electrons does neon have? It has 10. 2 on the first energy level. Because are you going to want to go to the 100th floor in a hotel if there's a room on the bottom floor? What if the elevator doesn't work? then you're going to want to do that, right? So we're going to lowest energy first, right? So then we have, so that's 2, 4, 6, 8, 10. And why do you pair them up like this? You want to know about that? You take the higher chemistry. How's that? Okay? All right, so now its second energy level is completely full. These guys are in the same group. These are noble gases. They're completely full. Do you see why that they don't want to react with anything? Because if they react, they're going to change the number of electrons on their outer level, or their valence shell, valence energy level. They're going to change, and they're not going to be balanced. It's kind of like a full tire going down the road. Nice and smooth, right? Everything's all balanced and nice. Well, you get one tire that's low of air. Yeah, come on, it's pulling the car to the right or whatever, right? So it's a little bit off. That's kind of what this is. And this kind of has a bulge in the tire. Fa-boom, 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 fa-boom. These guys are in group 1. And they're just saying, come on, get rid of that bulge. Get rid of that extra electron. Do you see why they're the most reactive? They just want to get rid of that thing so they can be like these guys, where they have a full shell. And they're nice and they're more efficient in energy-wise. Make sense? They don't really talk, but okay. So, and we can keep going. Sodium has how many valence electrons? So sodium is right below lithium. So this guy has 1 valence electron. This guy has 1 valence electron. You with me? In group 1, they all have 1 valence electron, and that's why they all are so reactive, because they just want to get rid of that one. So valence electrons, I'm going to have to take a break. Sorry.
Yeah, she used to sit with you. Is she in your lab class? Is she taking chemistry?
I would do it just for the sake of it. Not steel specifically, but.
No. With the white,
Visualize where it is.
with the white hair.
It's in the middle, right?
She used to do. I just tried her yesterday, she came in my, I was picking up the patient. I have this one, the other one is psychology. Do you have psychology?
I already did that.
You have.
Only I had to. I took penalty for Saturday, for Tuesday, Thursday class. And next class is not time. Yeah, how I used to do it.
Me too.
All right, sorry about that. So, how many valence electrons are in group 1? 1 valence electron. There it is. How many in group 2 do you think? 2 valence electrons. Right? Because they have 2 more than the previous energy level. We'll just keep counting. What's after? So in group 13, how many do they have? 3.
Three.
Whoa. Oh, because these are the main group elements,
They
right?
wants to get rid
These are
of
the main group elements. We can call this 1A, 2A, 3A, 4A, 5A, 6A, 7A, not 8, and 8A. And then these are the B group. Okay? But we can just look at that last digit. How many are in group 14? 4. How many are in group 15? Oh, how many in 16? 17? 18? Except for helium only has 2 electrons total. It can't have 8. But why is it in that same group as the noble gases? What's the same between this one and this one? They're full. Their valence shell is completely full. And that's what makes it stable. That's what makes it inert. You with me? Okay. So we can only tell how many valence electrons are in the main group elements. We can't tell right here and here. We'll learn how to do that next unit. Okay? But we won't have to memorize those. Do we have to memorize these? No, just look at the periodic table. Know how to read the periodic table. Are we good? All right, any questions with valence electrons? Okay, now let's talk about electron configuration. Kind of started there, but that's kind of got to know that first. So electron configuration. And the model that we have right now for the atomic model of the atom is called the quantum mechanical model. You guys know what quantum mechanics is? Physics. It's like modern physics. And it's talking about the really fast and the really small. And we're talking about, okay, light, you guys understand light, right? Light travels in a wave. You guys understand that?
Yeah.
But it acts like it's also a particle. And we call that the wave-particle duality. And that gets into quantum mechanics. Should we quit here? Okay, so that's quantum mechanics. And this electron configuration kind of deals with quantum mechanics, saying we can't tell exactly where that electron is and how fast it's going at the same time. We can't. There's no way of knowing that. And we call that the uncertainty principle. Again, quantum mechanics. We'll stop, okay? So this electron configuration is more about that when we get a little bit higher in our knowledge, okay? So if you want to go deeper, then you'll learn more about that. So I'm going to show you how the electron configuration is. If you want to just sit back and enjoy, go for it, okay? All right, so the electron configuration for hydrogen is going to be 1s2. Now this is just a code. You guys remember when you was a kid, you have your club and no boys allowed or no girls allowed, right? And you have your buddies and you make your own code to where only you guys, only people in the group can read it, right? You guys do this? You're crazy. Okay, whatever. So sometimes we did that, right? And I remember my sisters did that. I never did that because I was born between sisters. And I was like, well, I want to, right? And I even played Barbies with them because I had no friends. So, played with the boy Barbie, though. Okay? Ken. Okay. Sorry. That was off topic. All right. Here we go. So this is basically all this is code to help us to know where these electrons are. Well, why do we need to know where the electrons are? So we can understand what? Their properties. Because the electrons determine the physical and chemical properties of elements. You with me? And that's all we need to know about it for this class. But this 1 represents the energy level. This S represents the subshell. What do I mean by subshell? This is the S subshell. That's the shape. And this one over here, this is the P subshell. That's the shape. Okay? And this 2 represents number of electrons within that subshell or within that orbital of electrons. Good? And if we look at the periodic table, it has 1 electron. And we're talking about neutral atoms right now, right? It has 1 electron. And what energy level is that electron in? Energy level 1, because it's in the first group, right? And it's in the S subshell. Let me bring this up real quick. Another periodic table, and again, I'm not going to test you on this, guys. Just enjoy. Then why are we talking about it? Because it kind of helps us to know the properties a little. Anyway, so here's the S subshells, these first 2, along with helium is also part of the S. The rest of the main group elements, that's the P. So we'll call this the S, this the P, and then we got the D is the transition metals, and the F are the intertransition metals. Now, we're not talking about the elements themselves here. We're talking about the electrons around the elements. You with me? Okay? So we can use this periodic table to come up with all of this. So let's think about the electron configuration for helium. It's in group 1. That's energy level. So not group 1. Period 1. So it's in energy level 1, right? And it's a part of the first 2 electrons are part of the S orbital, right? Or the S subshell. And how many electrons are in that 1s? Count them. 1, 2. So that's the electron configuration for helium. You with me? I'll do a few more, and then we'll stop. If we go to lithium, so lithium is going to be 1s2. Why do we start with 1s2? Because the first 2 electrons are on the first energy level. You can't just, okay, I'm going to put my first electron on the second energy level. Can't do that. You got to fill the first energy level first. Okay? So the first, so again, think about this table as the table of electrons instead of elements for a minute. So the first 2 electrons are on that first energy level. And they're both in the S subshell. Okay? So it's going to start with 1s2. And then we go down to energy level 2. And this third electron is also in the S subshell. But there's only one of them. So that's the electron configuration for lithium. Are we following? And I'm going to skip over a few. I'm going to go to oxygen. Oxygen, what are we going to start with? 1s2. Then after 1s2, then we got electron numbers 3 and 4. That's a part of energy level 2. Still the S subshell. Because these are the S. This is the whole S group. You with me? And there's 1, 2. So that's 2s2. Well, basically, that's the electron configuration for beryllium, isn't it? Then we move on. Oh, now we're in still the second energy level, so energy level 2. This time subshell P. And how many until we get to oxygen? 1, 2, 3, 4. That's it. Oh, we just keep going all the way through. Don't freak out about this. Please don't. Are we okay? And there's some exceptions and some little twists and turns as we go deeper and deeper, but we're not going to. Okay? So that's the electron configuration. It tells us kind of where these electrons are, and it tells us, okay, that helps us to know what the properties are. Does anybody want another one? No? Okay, let's move on. So if you look at the electron configuration for hydrogen is 1s1. So how do these guys, what do these guys have in common? They have one electron in the highest energy level. We call that valence electrons. Okay? Any question before I move on? Yeah, Andrew.
I'm not sure I caught any of that, but are subshells
That's like the
kind of
shape.
the same as shells in a way? Because if we're talking about the second energy level.
Not quite, because there's an S and the P within that second energy level, right?
Okay.
And we're going to be talking about D and F too. Well, we won't, but, right? So it's really the shape.
Okay.
And if you want to look at the shape, you can look it up on the internet. What are the shapes of F? Because I can't even draw a D, guys. Well, I probably could if I really practiced, but I'm not going to, okay? Yeah, Chap.
Do you expect us to know kind of the format, the 1s2, the 1s?
No. What I want you to know is if they're in the same group, for main group elements, they have same number of valence electrons, and that's why they have similar properties. Good? Because if these guys, if group 1, they just have one valence electron, they're dying to get rid of it so they could be, right? That's why they're so reactive. And even in the transition metals, these guys right here, why their electron configuration makes them conductive, we're not going to need to know that deep. But they have the same number of valence electrons. Well, not really. We'll get there. Okay. Does that make sense? Any other questions? Okay, the last thing we want to talk about today, so we'll finish this before break. We'll have break. We'll come back, and if you guys have questions on the study guide or anything else, then let's do that, because we got a test that's
Next Tuesday.
due by Monday. Okay, and let's see. Yeah. Are we good? All right. So you've got to take it in the testing center, so schedule a time to take it there.
1 hour or 2 hours?
You get 2 hours.
2 hours.
On average, it takes 1 hour,
Does it allow you to
but you get 2 hours.
You can take
because
this.
sometimes it gets submitted by itself.
It what?
It gets submitted by itself. It happens to me one time in testing services.
These studies
Like they
second
allowed
time
me
she
2 hours,
has experience.
but in 1 hour it got submitted
Huh.
by itself. So
In this class?
not in the stuff.
It should. Yeah, you get 110 minutes, not quite 2 hours. So you get 110 minutes to take the exam. It's 20 questions. So I would get really good at this, study hard, get ready for this. That way when you go and take the exam, You got it, and it doesn't take 2 hours, right? Because my experience, and this isn't always true, there's always outliers, right? My experience is the longer people take, the worse they do. So understand your material well enough before you go into the exam so you can just knock it out. Now, having said that, don't rush it. Please don't rush it. That's where we make mistakes. I do it all the time, and I've probably made some mistakes in this class already, right? Yeah, because I'm going too quickly. If you go too quickly, you're going to do the same thing. You're going to make mistakes, okay? Anything else? Yeah, certainly.
Real quick, so going back to the.
Electron configuration? Uh-huh.
So like sodium would be 1s2, 2s2, 3s1, right?
Not quite. You got to go in number order. So sodium is 1s2, 2s2. Then what's after this one? We got to go to the p. The fifth electron is still in energy level 2, but the p subshell, and if we count it, there's going to be 6. And that counts for 10 of them. If you look at this, 2 plus 2 plus 6, that's 10. And then sodium is on 3s1. But the highest energy level has one valence electron, one electron. And if you look at oxygen here, the highest energy level includes both of those. Energy level 2, they're both energy level 2. So it has how many? 6 valence electrons. Oh yeah, we know that. Oxygen has 6 valence electrons. Make sense? Thanks for asking. Anything else?
Do we have this question at the exam?
Nope. You do need to know valence electrons and similar properties in the same group. Okay. and good. I'm glad because questions are great. They are great. Okay. So let's move on to trends on the periodic table. This kind of helps us to know a few other properties and kind of how they change on the periodic table. Let me pull up another one. And if you guys want another periodic table, you can come and grab one, or you could just write it in your notes or whatever, okay? Okay, we're going to talk about 2 different trends. There are more, and we're not going to go too deep, so basically, yeah, just a couple trends. So the first one, and I'm going to make this a little bit smaller so that I can use different colors in the black. Yeah, right there in that binder. Okay, so the first trend we're going to talk about is atomic radius, or in other words, the size. You guys understand what a radius is? We have a circle. It's the distance from the center to the outside, right? So atomic radius is the distance from the nucleus to the valence shell. You with me? Or the furthest away electron. Okay? So that's basically the size of the atom. And let's see. As
You can see the atom, how they are thinking about the size.
because we can, right? Because we understand a few other things, so we can put this together. So as we go down the periodic table, what happens to the size, would you think? Gets smaller, gets bigger, stays the same?
Bigger, right?
Bigger, because more energy levels, right? Gets bigger and bigger and bigger. So the size increases as we go down. Now that's pretty straightforward. The next one's not as straightforward, so let's make sense of it. As we go from left to right on the periodic table, it decreases. Now, it's the same shell or the same number of energy levels, so kind of seems like they should stay the same, right? But these guys are physical objects, physical particles, right? So they have to follow the laws of physics. Now, if we take a magnet, for example, big neodymium, one of those big strong magnets, right? Doesn't have to be big in size, but just a strong magnet, right? And then you get one of those fridge magnets, one with those little letters on it and stuff. Those aren't as strong. You with me? So if I come over here and should have grabbed my magnets, but I didn't. Okay? So I have my keys here, and I put the neodymium magnet here. Well, if I hold it this far away, what happens? Is it going to attract? We won't see anything, but it's still there. It still has attraction, but we won't see anything. This won't start moving because it weighs too much, right? We still have to get that pretty far down and then thump, right? But if we get that fridge magnet, and it still might not pick it up, but okay. But it tracks a little bit, right? So that magnetism is the strength of that force. Well, there's another force that acts just like magnets, and it's called the electrostatic force. And we're talking about charges here. So we have the electrostatic force. That's what holds our bodies together. Okay, it's a pretty strong force. And what's going to have more electrostatic force, lithium or fluorine?
Fluorine,
Why?
because it has
More
more protons.
protons. Its nuclear attraction is going to be stronger for fluorine than it is for lithium. So what's it going to attract? Those protons attract what? The electrons out here. Kind of pulls it in a little bit tighter.
But they never touch.
Yeah, they never touch, but it pulls it in a little tighter because it's stronger. Does that make sense in everybody's mind? Chad?
That's why the size decreases.
Yes. And there are some exceptions, guys, and if you look at tables in your book, there are exceptions. We're not going to talk about those exceptions in this class. If you want to learn about it, take 1210. Okay? I teach in a few hours, so if you want to stay and learn, no. Okay, are we good? So that's why the size decreases from left to right. Your left to right. Good? All right, that's one trend. You guys understand what trends are, right? What's the trend these days? Anything goes, right? You guys ever get those, anybody into, what are they called? Air Jordan shoes? Well, back in 1985 is when they come out with their first pair of Air Jordans. And what do they look like? They look like the Air Jordans today. Exactly the same. I looked it on the internet. They're exactly the same. Exactly. Like, that's weird. So anything goes. Right? People wear bell bottoms today. That was back in the 70s thing. That was the trend in the 70s. Did everybody wear bell bottoms in the 70s? Probably not. That was a trend. So just like all trends, everybody doesn't follow the trend. But a trend, that's generally what happens. So in this trend, that's generally what happens. There are some that don't follow it. But does that make sense? That's what we're talking about, just a general trend. Okay? Okay, and the next one we're going to talk about, and the last one we're going to talk about, let me pull up another periodic table so that it's not messy. This one I'll do in blue. This one is electronegativity. And we will use this one in this class further on, okay, for the rest of the semester. So know this. So electronegativity is the ability of an atom to accept electrons, but only during a chemical reaction. The ability of an atom to accept electrons during a chemical reaction? Because they will not accept electrons if it's not a chemical reaction. It's not going to happen. That's why we don't get shocked on anything, right? So the electronegativity is the ability of an atom to accept electrons during a chemical reaction. So the higher the electronegativity value, the more it wants those electrons. You with me? All right. So now let's look at these trends here. Any questions on that definition? Okay, so if we go from left to right on the periodic table, what would you think happens if everybody wants to be like a noble gas? Which one do you think wants to accept the electrons more?
The one that has less or more.
Lithium or fluorine? Fluorine wants, because if you draw the, so here's fluorine, has 1, 2, 3, 4, 5, 6, 7 valence electrons. You okay with that notation instead of drawing the circles? Okay. It has 7 valence electrons, and how many does it want?
One.
Oh, it needs one more. Do you see why halogens are the most reactive nonmetals? They're just one away. They need one more to be like those noble gases. So it's going to try to get one more. Lithium, what does lithium want to do? It wants to get rid of that one electron. So if these guys come close together and you get enough energy, he's going to say, anybody want my electron? He says, does anybody have an extra electron, right? It's going to come over here. It's going to make this one negative now because it has extra negatives. This one has less negatives, so it's going to be positive. You with me? Question?
So why is lithium trying to give away as opposed to accept more electrons?
Because it wants a full valence shell, and if we draw the diagram, the Bohr model for lithium, it looks like this. Now lithium can gain 7 to have a full shell, or it could just lose 1, and now it has
So it's like more likely.
a full shell, right?
More likely to just lose the one.
Yeah, because in general, think about us. We're not going to do something if we can do it using less energy, right? Okay.
I have a question. Why
Uh-huh.
this chem, when the shell is full, it's getting negative, the one that losing is getting positive?
Because if it loses a negative, so all atoms are neutral to begin with. That means their charge is 0, right? And what does, when we say it loses, do we mean add or subtract? Subtract, it means lose, right? We lose an electron. What's the charge of an electron?
Negative.
-1. Not just negative, but -1. We lose 1. What's 0 minus a -1? +1. But if we say, okay, now we're fluorine, and we're neutral, but now we gain an electron, we gain a negative, that's -1. You with me? Yeah. Make sense? So as we go across from left to right on the periodic table, we can see the electronegativity value, the ability to want to accept those electrons, goes up, right? So it increases. Does that make sense to everybody? What about going from top to bottom? We know as it goes from top to bottom, it gets bigger and bigger and bigger and bigger. Let's think about our magnets. We have, go ahead.
She has a question.
No.
Okay, so if we look at lithium, has atomic number 3, so it has 3 protons. And we look at francium, it has 87. Which one's a stronger magnet? Francium is, right? But to the nearest electron, this far away. Here's the nucleus and here's the outer shell, right? Is it going to attract it? Not as much as if you have a smaller magnet closer. You with me? So as you go down, the electronegativity value decreases. Make sense? So which element on the periodic table is the highest has the highest electronegativity value? Seems like it would be helium, right?
Or neon.
But think about helium, neon, all the noble gases. Do they want electrons? No, they're perfect. Yeah, fluorine is the most electronegative element on the periodic table. And it has a value of 4. Do you need to memorize that? No, if you look at your periodic table that you get for the exam, you get the electronegativity chart. It gives you the values. You probably won't need that for the first exam. Well, other than this trend thing might be useful, right? But for the next exam 2, exam 2? Yeah, exam 2, you'll need it. Are we good?
So it's for the highest electronegativity
Yeah.
value?
All right. I'm going to go over one more thing. We'll talk about this next unit as well, but we've kind of been talking about it a little bit, but I didn't give you a name for it. The octet rule. Uh-oh. What does oct mean? 8. Octet, what elements have 8 electrons? The noble gases, right? Group 18 has 8 except for helium has 2, but it's still full, right? So octet means, octet rule means, let's tell you what it means, okay? Atoms will gain, lose, or even share electrons. And when I say electrons, I'm talking about valence electrons. Will gain, lose, or share electrons to achieve the electron configuration of a noble gas. And not just a noble gas, no, not a Nobel, noble gas, the closest noble gas. Closest.
To achieve the electron configuration.
Mhm. So basically has a full valence shell, right? Yeah.
So when you talk about sharing, would that be like a covalent bond?
Yes. Yep. And gaining or losing, that's an ionic bond. Yep. Perfect. And we'll get into that next unit. Any questions? All right. If there's not any questions, that's it. And the bell went off for the break already. I just wanted to finish all that stuff. Take a break. Okay. And for the next half, we're just going to review. And if you don't have any questions, I don't know what to review. So if you're good and you're ready for this exam, you could even just leave. But if you have questions, I would stay. Yeah, Andrew.
Sorry, what we're talking about valence electrons, I know in biology that if, say, it has 4 in the valence shell, like it's more like, so if it needs to lose or gain 4, it's more likely to lose or get loose.
It's more likely to share.
To share with 4. Okay.
It won't lose or gain.
Okay.
Carbon and silicon, I think they're only in covalent bonds, so they will only share.
Okay. For some reason they told us that it's more likely, I want to say it was a gain, but
Yeah.
I don't know what the logic was behind that. Okay.
maybe there's a condition where it will gain or lose,
Okay,
and maybe there's a rule for that.
but are we gonna come across
No.
this?
Out of the 16 years teaching, I never did.
Okay.
But I've just taught low-level chemistry. So I'm teaching 1210 for the first time this semester. So we'll see. Yeah. Why does it decrease? So you're going to have to use your imagination here, right? Here's a strong magnet, and here's a weak magnet. So with fluorine compared to lithium, which one's the strong magnet? Fluorine is. Why is fluorine the strong magnet? Because it has 9 protons, and the lithium only has 3 protons. So positive 9 will attract electrons more than positive 3. Do you get that? So they're on the same level. That means there's the same distance away from those electrons. But if you put these 2 magnets here, which one is it going to attract to the most? The stronger magnet. And so for fluorine, it's going to pull it a little bit tighter. A lot? No. But it's going to be a little bit smaller in general. Does that make sense? Thanks for asking. Yeah. Oh,
So I was looking for to do the test. Is there any way we can do it on a Friday?
they're closed on Friday, unfortunately. Yeah. Is there no other way to do it?
There's like a Monday, but I work.
Okay. Here's
class.
another option. I'm not gonna announce it to everybody because I want everybody to take it on that schedule if they can. But there's another student who says, no, can't take any tests for some reason. If you want to take it on Tuesday, right after this class, I'm here till 2 for the next class. I know that's during lunch, so just bring some food with you or whatever, and take it in here. So bring your, is this what you do it on? Would you do the test on this?
Yeah. On my
So,
computer.
yeah, bring a computer or whatever you're gonna do though. Bring that with you, make sure it's charged, and then we'll just take it in here.
Okay.
Does that sound okay?
Yeah,
Or do you have
That
another class
sounds-
right after this?
I do, but it's like in 30 minutes, but it's a lab,
Okay,
a chem lab.
okay, so
It should be-
whatever, if that whatever works better for you. But I'm gonna be here because other students said that they want to be
That
here.
would work good. I can miss a couple minutes in that class. I wanna
Okay,
get this exam done.
yeah,
Thank you.
yep, yeah.
And that's why I was kind of freaking out. I would go to see. Friday, Saturday, Sunday. Sunday. And it's 12 hours, so 6:30 a.m. to 6:30 p.m.
Yeah, like maybe I'll just announce it. And if people want to stay, they can.
And yeah, but I think I'm in the same chemistry level.
So, I know that's not cool, but, the only other time we do it is right now.
Yeah.
But, and I didn't want to do it right now, I wanted you the time to study it. So, yeah, I'll bring that up. With our review. Any questions? Andrew?
While we're on the subject, is there anything you'd recommend we write on that part, or?
Yeah, here's what I would do. You guys picked up this study guide, right? You guys know how I made this study guide? Went through the exam and says, you need to know this. You need to know this. Well, what should you write on your reference card? The things that you're a little bit shaky on, right? And you can put everything on there if you can fit it, write it small enough and still see it, but if you're asking me what I would write on it, nothing. But, so we're all different, right? Sorry, I know that's probably not a great answer, but anything else?
I struggled last class with the, like atomic mass, like the ZAC, what it
Uh-huh.
does, and there's a question on the homework where we had to work backwards.
Yeah.
Can you go over that?
Yeah. And if you have questions on your homework, maybe a specific question says, what about this? Yeah, bring it up. So, first thing I heard was atomic mass. So, calculating the atomic mass?
Well, I think one I had a hard time was, I don't think I wrote the formulas down right, and I think I put
Like for-
technically like Z, well, Z equals the number of photons.
Uh-huh.
But I think for the atomic mass, I wrote like, that is the number of neutrons, and so I think that's why I got mixed up.
So, the atomic mass is not that. So, the mass number, you get the difference between mass number and atomic mass? Atomic mass is on the periodic table, and that's the decimal number. That's the weighted average of all of the mass numbers for the isotopes of that element. Okay? So, mass number is A. On this symbol, that's what A is. And what does mass number equals? The number of protons plus the number of neutrons. Good? Because basically that's the mass of our atom. Because the electrons are basically massless, right? They're not, but basically. And then Z, that's the atomic number. And that's the number of protons. So if you know the atomic number, you know the number of protons, then you take number of neutrons is equal to A minus Z, if you wanted a formula to memorize. Okay? And then C, C is equal to the number of protons minus the number of electrons. That means the number of electrons is equal to Z minus the charge. If you wanted a formula. So here's two formulas you could use.
Formula for finding the mass.
No, this is not the mass. This is finding the number of protons, neutrons, and electrons. Is that what he was asking, right? Yeah.
Neutron.
So how do you find the number of protons? It's just Z, right? The atomic number of that element. Good, that's going to be on the exam.
Okay, so I asked this, the number of electrons, like assuming it's neutral, it's just the same as protons, right?
Yeah, if they're neutral, they're the same, but you can still use this equation. If it's neutral, then it's whatever Z is minus 0, which is Z, which is the number of protons. Does that make sense?
Yes. And if it were neutral, C would be just 0, or would it be?
There wouldn't be any number. It'd be blank. No charge, no nothing.
I almost gave that up. I wasn't sure what to put. All right.
Good. Yeah, Mariana.
Well, that was a question about something else. Okay.
Yeah, are we done here?
I think that's sufficient for now.
Okay, perfect. Yeah.
So in the, when we classify matter by properties, you said there's physical and chemical.
Which one are you looking at?
Well, just
Oh, okay, just a different one.
the physical properties. Is that all about physical properties?
Sorry, what's your question?
Oh, okay, so my question is, I didn't understand the intensive and the extensive.
Okay, okay. Okay, so intensive tells us what the material is. And it doesn't matter how much of it that you have, right? So for example, what is the color of copper? Brownish, reddish, orangish, right? That's the color of copper. Does it matter if you have a penny versus a ton of copper? No, it's all the same. It all has the same color. So that's an intensive property. But if you said mass, the mass of a penny is like in milligrams or grams, right? And the mass of a ton, well, is a lot. So does the mass tell us that it's copper? No, it just tells us how much we have. So if we have 1 kilogram, it doesn't mean it is copper, right? So that's extensive. It depends on how much you have, not what it is. Does that make sense or no?
So when it comes to melting point, I said that was
Okay. It's intensive
oh, intensive.
because water melts at what? 0 degrees Celsius. Or ice, which is another word for solid water, right? Melts at 0 degrees Celsius. It freezes at 0 degrees Celsius. So that is also basically the same point, right? What about boiling point of water? 100 degrees Celsius. Does it matter how much you have? No, it boils 100 degrees Celsius. And that's at sea level, but so that's intensive. Make sense? Is that clear? Do you have any other questions on that? So, yeah, go ahead.
My question is, this confuses me, how to navigate the CHEM campus page where to find different components. Even this one has on the exam,
How to navigate what?
like chemistry,
If it's on this list, yeah, it's on the homework, or it's on the exam. Number 30 says know how to navigate the Chem 1110 Canvas page and where to find different components. Yeah, know how to do that.
Even it's on exam.
Yeah. Know how this class runs on Canvas. That's going to help you the most. Well, not the most, but it's going to help you a lot.
And question number 20, we can explain a little.
Number 20, and then we'll get Chad's question. Okay, number 20 says, what are the 3 subatomic particles of an atom? What are they? Protons, neutrons, electrons. And you need to know where they're located, and you need to know their properties, right?
Yeah, that's what
Where's a proton located?
it's inside.
In the nucleus. What about neutron? Nucleus. What about electron? Outside the nucleus. Good?
Determine the element of an atom, proton, neutron, electron.
Okay, Chad, did you have a question?
Yes, could we go over number 6?
Yeah, number 6.
Yes, that was my last.
What is the difference between a mixture and a compound? So if we have H2O, is that a mixture? Is it a mixture of hydrogen and oxygen?
No,
How do we know it's not?
because
Here's why. You cannot separate them physically. A mixture is a combination of different substances, two or more substances, that can be separated physically. How do we separate them? Filtration, that's differences in size. Distillation, differences in boiling point.
Configuration.
And we said centrifugation, right?
Oh, centrifugation.
And that's differences in density. Magnetism, difference in magnetism, I guess, right? Or differences in physical properties. That's how we do it.
Whereas to separate those two, we'd have to use chemicals.
That's right. We'd have to give it energy. Yeah,
So basically a compound can only be separated chemically.
that's right. Compound is a pure substance, just like elements are pure substances. All other substances are classified as mixtures. Yeah, Emma.
For the external properties of the different states of matter, is that like the same definite shape and volume of solid, or is it talking about like physical property?
What number is this?
That's number 3.
Number 3. What are the 3 states of matter? Yeah, that's solid, liquid, gas.
Yeah,
And then it says, and their specific properties. Yes, that is definite shape, definite volume, all that stuff. Yeah, so solids have definite shape, definite volume, right?
Yeah.
Liquids have definite volume, but not definite shape. And gases, no definite anything. Good?
What is the difference with, again, number 6, what's the difference ways to separate mixture, number 7? Like, what is the difference ways?
So we talked about that. We have filtration. It's basically, here's the broad answer. If you can find a difference in physical properties, you can separate them with those differences. So filtration is difference in size. Distillation is difference in boiling point. And centrifugation, use a centrifuge, that's a difference in density. Centrifuge. Centrifuge. Do you know what that is?
It's a centrifuge, they put the blood in.
Yeah, Yeah, it separates because they have different densities. Yep. Yeah. Anything else? Yeah, Chad.
Could we do a few conversions from like metric to American?
Yeah, metric to American. Do you want to do metric to metric at all?
Which one
I
is?
feel pretty confident that.
Okay, so we'll do metric to American.
How do you recognize that metric? This is metric to metric and this is metric to American.
Okay, American unit is like
LB.
feet,
Feet.
inches, pounds, what else? Gallons, miles. All those things we only use in America. Right? If you have a unit that you don't use in your country, it's probably American.
Pounds, you said?
Right? And I will give you the conversion factor for that. On the exam, I will. Anything to do with American, I'll give it to you.
Okay, and what
The only
about-
things I will not give you are the prefixes, the conversions from metric to metric. You have to know that. Either know it in your brain or have it on your reference card. But if you do have it on your reference card this exam, still get it down. Because we got to know that for the rest of the semester. Okay? So let's do, what, does it matter what?
Let's do the last one on that, like first worksheet we got, recommendation.
Yeah.
This says a doctor orders a 50-pound child to take 75 milligrams paramycin every 8 hours. How does this amount compare to the recommended dosage of 2 to 2.5 milligrams per kilogram administered every 8 hours for patients with non-renal illness?
Okay. Since they're both per 8 hours, Do we have to worry about time? No, we can just get rid of that. Does everybody understand that? It's the same rate. If it wasn't, we would have to include it. Okay? All right. So we want to compare it with this. That means we better know what our dose is in milligrams to kilograms. Does that make sense? And right now we have pounds and we have milligrams. This is the milligrams, so that's that part. So we got to change pounds to kilograms. So 50 pounds, and I would give you this conversion factor, 2.2 pounds, or I might give you something else, but it's going to be the right conversion factor. I would use what I give you, because if you use this one, like, yeah, I know what that is, and you actually get it wrong, because, I remembered it wrong. That happens, right? Use what I give you. 2.2 pounds to 1 kilogram. This is the only one I know on my brain. I think the one on the exam is like 0.4 something.
1 pound to.
Yeah. But it's the same thing. So pounds goes away, and we know to put it on bottom so that they cancel, right? And then that's going to be close to 25-ish.
Yeah.
No.
Now we put the 50 over 2.2 divide.
So what is 50 divided 2.2? Yeah, 50 divided 2.2.
I had to.
22 point.
7.3.
Yeah, there is another way to do it. And that's how many kilograms, right? So now we want milligrams per kilogram. Well, we have milligrams right here. 75 milligrams per 22.73 kilograms. Are we in the right unit? Yeah. Then we know we did it right.
So that means 75.
Do you want me to show you the way I go about this? This is milligrams of drug per kilograms of body mass, right? So I just said 75 milligrams of drug per 50 pounds of body mass. That's really what it is, right? And then 2.2 pounds to 1 kilogram. And now I have milligrams to kilograms. Is that the same thing? It is. So is there more than one way to do these, guys? Yeah, I started with something different than I started this time. But either way, so follow the problem-solving strategy. Know what we're looking for with units. Know what our units are. In this case, we're looking for milligrams to kilograms. So make sure we end up with that. Okay, is this my answer? What's 75 divided 22.73? 4 point something? And we just got to compare it with this. Maybe it's 3 point something. I don't remember. 3.2. Okay. And so we're going to compare it with the average dose. So what is it? It's more. It's more than the average. That's all we're supposed to do on that particular one. Uh-huh.
What's the answer for this?
More than average.
So it's 75 multiplied.
Well, it's 3.2 milligrams per kilogram, which is more. Because remember, you got to go back to the question. What is the question asking? In this case, it's asking just to compare it. That's it.
So this is a metric to American?
Well, this one is American, so I will give you this conversion factor. Yes. Yeah.
Do we have to round up?
Great question. In this one, did we have to? No, because this is not my answer. My answer is more than average. That's my answer in this problem. But yeah, should you round? If we was looking for this, did we get 3.2 exactly?
It was like 3.29.
3.29. And we want to know, maybe we're looking for this, okay, to the nearest decimal because it's 2.0 to 2.5. So that includes 1 decimal, right? So maybe we should know for 1 decimal. So yeah, we would say 3.3. Yeah.
To round it.
Does that make sense?
And
But don't get hung up on that. On the test, it's multiple choice, so what do? You look at your options and say, which one is it?
you do some calculation, then it's.
And if they round it slightly different than you, but it's gonna be really close. And I promise, I'm not gonna say, I'm gonna get them 3.2. Not gonna do that, okay?
In exam, we have the.
Does that make sense?
Yeah, so not too stressful.
Yeah, you don't stress too much about exactly where you round it. Just remember, don't round until the very end. So if you have multiple steps, don't round your answer until the very end. Good? Question?
We will have the periodic table or we will get one,
You will get one.
so we do not carry ours.
Yep, you don't have to take it with you. In fact, you can't take it with you. The only thing you could take in there is calculator and a 3x5 reference card.
Both sides.
Both sides. Yep. Yeah, Andrew.
So question 2, define the following. Is there a good place to find vocabulary on Canvas? I don't know if I've seen proper.
On Canvas?
Yeah.
If you're on Canvas, that means you're on the internet. You can find them there.
Okay. Well, because I always got this question wrong on the pretest. I don't remember if it was
Okay,
class,
let-
biology, but I always got mixed up between the law, theory. Can we go over those?
let me tell you what you need to know here. So, you need to know how to use the scientific process. And do you guys remember doing the bad science, good science, bad science assignment? Okay. Well, what determines if it's good science, bad science, or fraudulent science? It's good science if
Follow the scientific process.
good, and your conclusion or your results or what your what am I trying to say? I'll just say conclusion. Your conclusion is based off of what you tested, right? If I say, okay, I tested on these rats, and if you give these rats a certain medicine, a certain drug, it makes them smarter. Therefore, you can give these to people, and it'll make them smarter. What do you think? No, that's bad science. What makes it fraudulent science?
If they intentionally falsify data.
Yeah, we take our data and say, you know what? I'm looking for this number. I'll just tweak it just a little bit, right? Then it's fraud. It's not real. Make sense? So make sure you follow good science on the exam. And the scientific process, so we can talk about these. The law, what's the difference between law and theory? Almost nothing. Almost nothing, okay?
What would be
Uh,
the differentiating factor? Because
Maybe we don't have the technology to test it in a certain way. For example, the atomic theory. Well, this is what we know so far, but we don't know for sure because we can't see it still. Until we get technology to help us to see it, it's not law yet. And over the last few hundred decades or centuries, we've adjusted our theory, right? And what's a law? It means we've tested and we can test it in all ways, everywhere, and we know. We've gone to the moon, so we know how gravity works on the moon, right? We've had theories before we've done that, but it works. It works everywhere we go. Maybe if we get to Pluto, maybe it doesn't work there. We haven't gone there yet, right?
Or Mars.
Maybe we send probes there and it works, right? But, so do you think we can prove a law incorrect? Think it's possible? Maybe. We just haven't done it yet. So, until we do, it's law, because we've tested every other way. Does that make sense? Okay? And hypothesis is what?
What is it, like say something?
Our thought on what the answer or the solution to the problem is, based on our experiences, based on our knowledge, based on our research. Okay, this is what it is based on what I think. I haven't tested it yet, but I think this is what's going to happen. Is it bad if you get it wrong? No, this is how we know, right? So then you test it, you experiment with it.
Test and experiment.
If you have a hypothesis that you can't test, it's garbage. It doesn't help us, right? And test experiments, they're the same thing, right? Just a different word. All right, anything else? Yeah. 18. What determines the element of an atom? Number of protons. That's it. Yep.
And then 26.
So make sure you know that, right? Make sure you know that number of protons tells us what element it is. Number 26? Know the different groups of elements on the periodic table. I'm not talking about classes here, I'm talking about groups. So you got the alkali metals, alkaline earth, halogens, noble gases, transition and intertransition.
So those are the groups.
Mhm.
And what are the classes then?
Metals, metalloids, and nonmetals.
Okay. What we discussed.
Yep.
Okay.
Metal or non-metal?
Metal, metalloids, nonmetals. Yep. Yeah, Eric,
What all can we have on that, display?
whatever you want.
This may sound like a stupid question, for magnifying glasses.
I don't know what they would do. I'm sure it's okay. But what I would do if I were you, I would study that really well so that, if you understand it, then we move on, you'll still know it. And we're going to still be talking about some of this stuff, but just not directly. But we have to use that to do the other stuff. Then we move on, and you understand it all the way up to here, then you probably won't have to take the final. Or if you do, you're going to do well, with or without a reference card. No, but yes, you can have one. You can put whatever you want on it, however much, make it small, but just saying. Make sense?
Question number 6.
But I can't guarantee you that they'll let you have a magnifying glass in there. I don't know. I'm not saying you can't, but you might want to go ask them before you. And they're in the little library, right? Downstairs? Okay. Yeah.
Can you do the last two questions on this paper?
Yeah, what paper is that? Read the top.
The converting.
What number?
Reasons.
What section number? Very, very top.
Numbers, units, and conversions.
Units and conversions? Okay, let's see. So you want to do the last two sections?
One was just the last. I did-
Oh, so metric to metric?
Yeah.
Okay, yeah, let's do metric to metric. Or the last two, one of them is feet, inches to centimeters, right? So let's do that. And again, I will give you these if you need them. So we got 7 feet, 2 inches. And we got to convert that to centimeters. Are we good? So here we have 2 different units to measure one length. Let's change it to 1 unit. What unit do you want to change it to, inches or feet? Okay, let's change it to inches. That means we got to say 7 feet, and we got to convert that to inches, right? So 1 foot down on bottom so that it cancels. 12 inches on top, because that's what we're looking for. And that gives me 80, is it 84? 84 inches and 2 inches. So that means we have what? 86 inches. That's how long this is. You with me? And now we can convert, your question.
84 inches.
That's what 7 feet is 84.
What is that one? 2 inches?
Well, we have 2 inches more than 7 feet. So we add those together and we get 86 inches. Are we good? Okay. And then we know a conversion factor. In fact, you don't have to know this. I'll give it to you. 1 inch is equal to 2.54 centimeters. Well, what if we're doing these worksheets? Then what? Google knows them. Right? If you're at home, yeah, look it up. But on the exam, I will give it to you. And that cancels, and then we just multiply those, and we get our value. Does that make sense? Did I go too quickly in that?
It's metric to metric.
This one is not metric to metric. This one is standard American, feet and inches, to metric, centimeters. Good? All right, and the last one says 14.4 MCL to ML. What is MCL? Does anybody know?
Meter, centimeter to liter.
Microliters. And that's another way to write it.
To milliliter.
Why do we have MC? Because that's what they use in medical. And that's where you guys are going into, and that's why it's in here. Okay? But for science, that's what we use. So 14.4 microliters, and we got to convert this into milliliters. So where does do we want microliters in our answer?
Yes. Because down still.
No, we want milliliters in our answer.
Top and down.
So what goes on bottom?
Microliter.
Microliters. Do we know how to go straight from microliters to milliliters? If you do, you can use it. If you don't, then do what you know how to do. Microliters to what? Liters, the base unit, right? And do you want to use exponents or numbers? Like whole numbers?
Numbers.
Okay? So whatever method that you got your reference on you know your prefixes, that's what I would use. And I can show both if you want. What would you want me to do? Numbers? Okay. So micro is a millionth, right?
A millionth of
That means a million millionths make 1.
1 liter.
You with me? And so that goes away. We don't want liters in our answer, we want milliliters, so we keep going. What goes on bottom? Liters, milliliters on top. How many milliliters to 1 liter? 1,000. I would know that one, guys. That one we will use a lot, more than any other one. Does that mean you shouldn't know the other
So
ones?
14.4
No, you should.
14.4 divided by 1 million and get 1,000.
And times by 1,000. That's it. Because all the units go away except for the unit that we're looking for. That tells us we did it correctly. Yeah, Eric.
I have a question. Maybe this makes sense. Why would we do it for microliters, 2 liters, and then back to milliliters? Could we just move the decimal point like over there?
You could. That's why it says, if you know, you could. Is there more than one way to do this? There is. The reason I show this method is because this is dimensional analysis. This is the math we use in chemistry. So later on, this is our first unit. This is the easiest unit. And if you get dimensional analysis down, and you know it, you understand how to do it inside and out, we're going to keep using it. We're not going to, we are going to do metric to metric. Will we do this type of problem later on?
At the hospital.
We will not.
No, we don't like hospital.
You might do pounds to kilograms at the hospital,
So,
milliliters, maybe. And those are metric. Those are metric. You will use metric to metric, yes. Okay? Are we good? Anything else?
I have question number one, confuses me, sorry. It's what are sticks to scientific method, what are sticks to the scientific, what are not? If you can read it,
Steps to the scientific method.
If you remember the scientific method steps,
Then,
then you don't need to remember them all.
yeah. What's the steps? First step, make observations to notice, ask a question or solve, notice a problem, right?
Number one, two.
That's one. Number two is we make a hypothesis. We try to solve our problem or answer our question. Number three, we test it.
Test.
Thank you. And then number four, we analyze our results. And number five, we publish it and get peer reviews and just keep
Yeah,
going.
we didn't publish.
Yeah.
I have a question
Number
number 7.
7?
Yeah.
Can we wait just a second? Sorry, guys.
Good luck. Is it okay?
Can I just ask, has anyone found definitions of like law theory and hypothesis? I don't know the difference between a test and an experiment. And I can't find it on
I think they're
Canvas.
pretty much synonymous. I wouldn't worry too much about it.
Yeah.
Well, I might say that and then you'll get a
No,
question.
sometimes
Yeah,
the main
because-
question
because like
confuses you.
Like, I can go back to this biology pre-quiz, like,
Mm.
an idea in science that is narrow in scope, is reasonable and testable, and serves as a potential explanation for an observed natural phenomenon is known as a,
Theory.
no. See,
Okay.
this is
Yeah,
why
I would've-
I'm
I
petty
would've
and
gone
like
for that one
annoyed,
too.
it's like, I
But
don't know
this
what
is
the
very,
answer is, they don't tell us. and I haven't
confuses
been able
us
to
an
find it.
exam.
I
There will be an exam,
have,
it will
from my
confuse you.
biology
I know.
class last semester,
Like the right
I
answer.
have some of them written down, I can see
Yeah.
if I can find those. and bring them in.
Yeah, that would be nice, cause I can't
I
find
can
it
message you
in
on
this
Canvas
class.
if I find them.
That would be awesome.
In an experiment, we use data to test, and in test, we give specific, like, what the outcome we get.
Okay.
So that's the major difference we
Outcomes. Okay. Yeah, I hope he doesn't have any tricky questions with those,
Well, then would.
I, like, and there was another question that was like, provides an explanation, and I was like, that's a law, right? Cause I think, I'm getting my classes mixed up, but one of them is like, if there's an explanation, it's a law. And then I answered that, and it was still wrong. So I don't know, that's why.
All right. What was your question?
The question of number 10.
Question number 7.
Oh, 7.
Yeah.
7 first, then 10? Okay, 7, what's the different ways to separate mixtures? So we mentioned this twice today.
Try.
So filtration,
Distillation.
distillation, and centrifugation.
Sorry, while we're on that, number 8 is provide examples.
Yeah, give example, each way to separate
Like
mixture.
how, can we just make anything up, like filtration would be a C?
Well, you can make anything up, but maybe they'll give you an example and they say, what type would you how would you separate this?
Like
right?
what?
Sounds good.
So separate sand from water, right?
Sand from what?
That's an example of how you can separate it, right?
Filtration.
And
is
filtration. What? Filtration,
Distillation.
centrifuge, uses centrifuge, right?
And what about the condensation?
The what?
Condensation.
Don't worry about it.
Because that's what confused me a lot.
Yeah, that's why I didn't talk about it,
We
because
were-
it's confusing.
Because I have skin.
And I won't test you on that one. Okay?
She and I concerning about question number 10.
Number 10,
No, I'm not concerned.
accuracy
I know what it is.
and precision. How do you know if something is accurate? It's close to the real or accepted value, right? It's close to the truth. And what's precision? How repeatable is it? Yeah,
How
See,
repeat
accurate's
is
more of
it?
a truth statement
yeah,
than imprecise is not a truth statement.
yeah. And precision, it could be truthful, right? But precision is how many decimal places can we measure it to? If we can measure it to the nearest thousandth of an inch, then it's pretty precise. If we can measure it to the nearest whole inch, not very precise.
Precise.
Does that make sense?
Precision, how repeated it is, or
How if you can measure something and get the same thing every time, or pretty darn close, then it's got high precision.
or get closer to it.
Yeah, if one time you measure it and you get 1.5 inches, and then you measure another one that's, I'll just say 1 inch. It's closer to 1 inch than 1.5, right?
We can read on the book this question and also Google it, but the way you explain it, it's much acceptable for me.
Good, good.
Because you are
No, thank
taught
you.
a lot and, so.
Yeah, Mariana.
On the worksheet, the numbers, units, and conversions, there's a question here that's.
Okay, yeah, let's do it.
Right here, I'm sorry. It's, I think Joseph,
Which number? Which one is it? What section?
there's, numbers, units, and conversions.
So section 2, you said?
Oh, yeah, section 2,
Okay, which one down?
the last one.
Okay, a typical dose of clonidine, that one? Okay, yeah, let's do it. So it says typical dose for this for children is approximately 0.12345 zeros, 1234513 grams per kilogram of body mass. You with me? So I'm just writing this down because this is a known value. What would be a more convenient way of expressing this in terms of SI prefixes? So what SI prefix will we use? That's really what we're saying here. So let's change this to scientific notation. Might be the easiest way to go about it. So how do we do that? 1, 2, 3, 4, 5, 6. We move the decimal 6 places, so it's 1.3 times 10 to the negative 6, because this is a small value. You with me? Okay. Now, what prefixes use 10 to the negative 6? Micro. So we should just say this is 1.3 micrograms per kilogram. Would be a much nicer way to write it. That's all it's asking. Does that make sense? Yes?
Yeah.
Okay. That's all it's saying. Use the prefixes to help us to make our numbers better. Yeah, Eric.
What are you providing that we don't need to write on our class?
This periodic table and this backside that I gave you one of these. If you don't have one, you can come and grab one. You don't need to take it for the exam. I will give you one, or they will give you one, right? But that's what I will give you.
I'm sorry.
Take a calculator, not your cell phone, to make calculations, and your little reference card and something to write with. Yeah, something to write. They will give you scratch paper as well,
Or whiteboard or something?
or a whiteboard. Yeah. Mm-hmm.
To have a question, I'm
Yeah.
sorry to asking this again, number 14.
Number 14. What is the formula for density and what are the derived units for density? So density equals mass over volume. So what are the derived units? Mass, what's the unit of mass? Kilograms, not grams, but kilograms. What's the unit of volume?
Pound LD.
Meters cubed. We was using liters, right? And I think liters is what you're probably wanting to use. Kilograms
Liters?
per liter.
Kilogram per liter.
But do you know why meter cubed is the SI unit? Because meter cubed is just distance times distance times distance. Length times width times height, right? Meters times meters times meters is meters cubed. But we don't use that a lot, especially in chemistry.
Kilogram to liters, like, is it?
You need density. So this is a conversion factor, really. We
For
can
example-
use density as a conversion factor.
How, like, for example, I have 1 kilogram, for instance, sugar.
Uh-huh.
How we change this to the liters?
You have to know the density of sugar.
Oh, I have to put in water and then,
No, you have to know the density of sugar. You can look it up. And will I give you the density if you need it? Otherwise, I'll give you the mass and the volume and you can find it, right? So watch, everybody listen. This is what you need to know. We're going to have a multiple choice, right? And maybe the answer is going to be measured in grams per milliliter. And if they give us 3 kilograms per 5 liters, can we convert that to grams per milliliter? Do we have to know the formula? We don't. Convert kilograms to grams and convert liters to milliliters.
yeah, that's possible.
That's it. Or maybe I don't know the volume and I know my density. Maybe it says this is in centimeters cubed. Ugh. Well, we know 1 centimeter cubed equals how many milliliters? 1 milliliter. They're the same. 1 centimeter cubed, or cc, if you're used to that.
It's volume inside.
That's
the
the
jar,
volume, uh-huh.
Inside the jar.
Yeah,
or
yeah.
Glass.
Yeah, and they're equal. 1 centimeter cubed is equal to 1 milliliter. We good?
Where do you use that in daily life? That's the kind of question. Centimeter cube.
Anything else? Yeah.
Can we go over the difference between homogeneous and heterogeneous?
Yes.
Which number? Oh, number 5.
So homogeneous and hetero. Homogeneous means the same throughout, right? So pretty consistent throughout. So what you need, so number 5 says, what is the difference between homogeneous and heterogeneous? So if I said air, what would you say, homo or hetero? Homogeneous, right? It's the same throughout. You breathe over here, you get enough oxygen. You breathe over there, you still get enough oxygen. Over there in the top corner, you still get enough,
It's
right?
homo?
It's basically the same throughout.
It's hetero or
Homogeneous. So air is, well, if I spell it right, air is homogeneous, but if I say
eating a mushroom or
a salad,
salad.
salad is hetero, because it's different throughout. One bite you might get mostly lettuce, one bite you might get mostly tomatoes. Good?
Here,
Does that help?
can we say hemo? Water is hemo?
Water?
Yeah.
Water is not a mixture. Water is a pure substance. What makes water a pure substance?
Oxygen and carbon.
You can't separate it physically. Yeah.
So it's homo.
That's not a mixture. These are mixtures. Compounds and elements are pure substances. You cannot separate them by physical means. You can separate them chemically.
But air also separate.
Air? Yeah, you can separate air physically. They have different densities, different boiling points, different evaporating points, whatever. Yeah, you can separate them. Does it mean it's easy? Maybe not, but it can be done.
Maybe we can separate it somewhere that there's no oxygen.
Yeah, you can. You can separate it. Yeah, Andrew.
This goes back to my first question about electrons and numbers and stuff. It's
Uh-huh.
on the very end of the last,
Uh-huh.
the latest worksheet. It says, tell how many total electrons each of the following atoms or ions has, and match the atoms and ions to the right. I did most of them, but for some reason, like potassium and magnesium, I got totally different answers, so
Okay.
I wonder if we could do that.
Potassium and,
Oh wait, sorry, not potassium, I take it back. Magnesium. So it's magnesium with the 2 positive.
uh-huh.
Yep. And then the titanium with the 2 positive. I think the rest I matched. No, that's a lie. Dang it. It's not magnesium, it's calcium, sorry.
That's okay, we'll do them all.
Thanks.
Okay, it says, tell how many electrons are in the following atoms or ions. So how many electrons are in magnesium 2+?
2 extra.
Ah, it's 2+, good. That means it has 2 less. Right? Now, if we look at the periodic table, here's magnesium, has 12 electrons. If we follow the octet rule, it wants to do what? To be like the nearest noble gas neon. It wants to lose 2 electrons. Or it could gain 6. Which is easier? Lose 2. So if it loses 2, we're going to have, well, regular magnesium is 0. It starts with neutral, right? And we lose 2 electrons. Electrons are negative. So loses a -2 total. That becomes +2. So that means, if you look on the periodic table, magnesium has 12. It lost 2 and became Mg2+. Now it has 10 electrons. You with me? And then you come over here to
That's titanium.
that's titanium. So let's just do them all. Calcium, if we look at the periodic table, calcium, what's the nearest noble gas to calcium?
Magnesium.
No, noble gases are on the right side of the periodic table. Look at your periodic table. This is how you would do this. So calcium is number 20. That means it has, well, it's all, actually, we don't need to worry about that. It's not charged, is
I
it?
just realized what I did.
It has 20 electrons,
I saw thallium.
right?
And I didn't realize, like, I didn't realize some elements
Okay.
that connect capital letters, so I just thought, oh, TI. And
Is that,
I was trying to calculate.
that is
thallium,
TI.
Not titanium.
Oh, yeah.
So that's.
Yeah,
why
the
I
second
was
letter is always lowercase. Okay?
like, oh, is it though on thallium?
Always. It's
Always.
TL.
That is now? Okay.
Yes, because it's always lowercase.
I didn't think it was one atom with another one.
What?
Or you'd think it was one atom with like another one.
I just.
Like CO.
Yeah, that's right. And you need to know that because when it's in a compound, 2 capital letters next together has to be 2 elements. Yeah.
I'm sorry, I have one question. I know you did explain, but there's a safe law, something already accepted, we have to follow the law, but there's a theory
There's what?
Theory, how we can define theory?
Theory?
I'm sorry, asking again.
Theory is something that is backed up by tons of evidence.
It's something that,
Okay, I found this on the web. For Siri is something that is backed up.
But like you said, use Google, right?
Um,
theory,
let's see. Theory
is
tries to explain. Oh my gosh. That's not going to help, but theory, no, is something that tries to explain why, and the law explains how.
okay. Try it.
That's probably the best
The best
differences between.
Try something, try to how?
So theory explains how something is, how a phenomenon works, how gravity works, right? Well, that's not a theory, but, and the law explains why it is the way it is. So we have a reason why, and theory we're just trying to explain, well, how is it then? We don't know for sure, but so how is it?
Like how
theory
something
is like
works.
a question and law is like the answer to question.
Okay, think of it that way.
But also theory, we can say something, how it works,
How?
how close it works or how it works.
But just because we know how doesn't mean we know why, right?
Law is,
Or what?
law is answering the how it works.
Yeah.
The law says how it works or how it acts.
The law says why it works.
Why?
Why it is the way it is.
Why it is.
Yeah. Yeah.
Can you do number 11?
Number 11, yes.
Number 11. And vice versa, this is something with.
It means, or other way around.
Oh, vice versa.
Okay? Know how to convert a number into scientific notation. So that's kind of what we did right up, where was it? Right here, right? How you convert it in scientific notation is right here. Or how to convert it from scientific notation back. Do you know how to do that? Okay, let's go through this.
All that part, I think you guys went through on last Thursday,
Yeah,
and I wasn't there.
okay.
Very last time.
So if we have, so let's take 0.00000013, okay? So the first step is we need to write the number, so the reason we use scientific notation is so we can make this a shorter number. Whether it's a big number or a small number. This is a small number, but it's still too long, right? So we want to make it shorter. So what we do is we move the decimal after the first non-zero digit. And the first non-zero digit goes right there. You with me?
And it's always,
From left to right.
okay.
Okay? So we're going to say 1.3, but we have to multiply this by 10 or else divide it by 10, right? In this case, divide. But we've got to count how many places we moved it. 1, 2, 3, 4, 5, 6 places. That means the exponent of 10 is going to be 6.
Negative 6.
But since this is a tiny number, this has to be a negative exponent. If we have a large number like 3600000, then it's 3.6 times 10 to the, here's the decimal, 1, 2, 3, 4, 5, 6. It's still 6, but this number is huge, so it's positive 6. Does that make sense? And then go back, you just do it the backwards way, right? You start here, okay, that means it's a small number, so we're going to move this decimal 6 places to make it look smaller. So we're going to move it this way to make it look 6 places smaller. And this one, we're going to move it 6 places to bigger, to make it look bigger,
One of the last.
because it's positive.
And for the 3.6, we put the point right there.
We always put the decimal after the first non-zero digit from left to right. So from left to right. So from this side over, our first non-zero digit is a 1 on this, so we do 1.3. Our first non-zero digit on this one is a 3 from left to right, so it's 3.6. Does that make sense? And we count how many places we move it. Yep. Don't worry about, yeah, we read from left to right. This is how we read, right? Sorry, you read from left to right.
The last question,
Okay. That helps a lot.
the last question she and I have, you're going to post this video by tomorrow? We can look at it.
Yeah. Yeah, we can do that. Okay, thank you. Any other, does that help?
Yeah, no, it did. My other question, since what are you providing, like meters?
Meters to certificate.
Yes, I will give you American to American, American to metric, but I will not give you metric to metric.
And how can I find what is the metric? It's very confusing.
Okay, look up, in fact, if you look up unit prefixes on the internet, look up unit prefix chart.
Is it possible to take pictures of the answers from the worksheet so I can don't?
They're on Canvas.
The answers?
Huh?
Oh, they are?
Yes.
Where do you find
That's
it?
why she asking me this, guys.
I'll show you.
Yeah, it has a spreadsheet on it.
And these are the ones that
There
you
is a
Those are the
mistake,
numbers,
way
uh-huh.
that we explain
And these are
it's
the
much
excellents. You can
easier.
use either one, but just make sure you put them in the right spot. Just make sure when you do a conversion factor.
we use this when you're doing
Correct.
what do you do, like sample, like 3.6
Like
kilograms
this.
to millimeter, like that?
Yeah, yeah,
Okay.
like this
That
right,
was my question.
right.
Because how do you know how you need to convert to
I'm from Turkey.
Yeah.
milliliters, and how do you know?
So this one right here is where we used it, okay? So microliter, look at micro, micro's right here.
Okay.
And if you look at the number, what number is it? 0.000001,
Yeah.
right? And that's 1 millionth, so we could put that, so we could do it this way. If we do 14.4 microliters, and we convert it to liters,
How do you know you have to
we can do
convert to
0.
liters? That's-
Because that's all that you know. You go micro, in fact, oh, sorry.
No, you
Can I look at-
no, you're
sorry.
good.
Let's see, micro. So if we count how many places, I don't like doing it this way because then I get confused, but
There could be
we
another.
go to 1 and then we go to this. We go to just, what was it going? From milliliters? Oh, we're going, so we go here and then we go back to here. But or we can say, okay, this is a difference of 3 decimal places.
You're taking it right now?
If you can see the difference between those is 3 decimal places, we can just move it 3 decimal places.
Is there another one? Is this a better example?
Yeah.
I'm just still very confused how you know
There's like 11, no.
Okay.
how to go.
So let me show you the way I think about it. Do you like these small decimal numbers? Yucky, right?
Yeah.
Okay, watch.
How would you order like from?
So 14.4 microliters. And if micro means 0.0001234 and 1, that's what it means, but that is equal to 1 over 1 million.
Okay.
That's what it is. So if we say we want to go to micro liters to liters, well, we say, okay, 1 liter, how many microliters is the same as 1? How many of these do we have to make this equal to 1? 1 million of them.
Okay.
1 million 1 millionths is equal to 1. Do you get that?
Yeah.
So 1 million, and this means millionth, 1 million 1 millionths. That's equal to 1 liter. 1 liter. This value has to be the same as this value.
Okay.
Another way we can do this,
If I just think about it in terms,
My lecture is.
okay, that's small.
And you know what to convert it because it tells us, right?
Well, it might not tell you to microliters to liters, but we want to
Or
go,
that doesn't, that then.
we
oh,
want to
okay.
go, we want to go to milliliters, let's say, right?
But it will tell us we're trying to go to, you know.
Yes, it will.
It will tell us, but it won't tell us that this, that's this decimal. That's what you're saying?
Yeah, I won't tell you this.
Oh, okay, okay. I thought it was like what we're trying to
Yes,
convert.
I'm not gonna, yeah, I will tell you that.
Okay, you're like microliters to liters. That, okay, but I need to know this.
Yes,
Okay.
and you need to know how to use that. So do you want me to show you using the exponents or no? Like,
Yeah,
okay,
at least to know both.
okay, microliters to liters. Micro, so 1 microliter is the same as, micro means 10 to the negative 6.
Okay.
So 1 10 to the negative 6 liters is the same as 10 to the negative 6 liters. Do you get that?
That was a more confusing.
Okay, but either way, they're the
The
same
other
thing.
one's more easier to understand.
Okay, then do it that way.
Okay. But it should, did we list it, like, these ones, last class?
It was a couple classes ago.
Okay. Would I be able to find them on, like, videos, or?
On the video that I posted on Canvas, yeah.
Okay.
But if you want to take a picture of it,
But there are too many options, and I'm looking for the options. I will see.
just the
I
right
will
one.
be shadow an practitioner
Oh, where is it? There it is.
And this is what we need to,
Yeah, you need to know these values or these values. They're the same.
okay. So that's when you're saying like,
but it's a
And these are the only ones. So on that one it has hemto and hecto. That we
yeah,
don't need
you
those.
don't need. Okay. And so, using the example again, so you say milliliters, so it's this, oh wait.
Originally in the past, 60s, 70s, they moved from chocolate.
So we're going from microliters. It could be grams. It could be liters. It could be meters. Whatever. We're just looking at this.
Oh, just the
Micro.
first letter.
Yeah.
Okay.
Micro to milli.
But I visited
Micro.
a lot
So
of
if we look at this,
shower, I was
there's
in lower
it's 3 decimal places different, right?
Yes.
This one's smaller, this one's bigger.
Yeah, Robin Pretty.
So if we have this, then we're gonna make it look smaller or bigger.
I'm sending my wife.
And that's why I don't teach it that way, because then you just, oh, what is it, what is it? Right? This is why I use dimensional analysis. So microliters, so micro is 1 millionth, so we need 1 million of these things to make 1 liter. Make
And
sense?
liters, obviously bigger.
And we're going to here, right? Going to the base, always to the base,
But she
Okay.
doesn't have to.
okay? And then, I don't want liters, I want milliliters. Well, milliliters is, how many of these do we need, 1 gram or 1 liter? 1,000 of them, 1,000 thousandths.
Okay.
So if we have 1,000 milliliters, that's 1,000 thousandths, that's equal to 1.
I never told my mom.
Okay.
Does that make sense?
Okay, yeah.
And that goes away and we're left with milliliters.
Okay.
Do another one?
Yeah. One more.
Okay.
I have a question.
Yeah.
I talked to you related to what, when is it? I forgot.
We're gonna take it right after class next Tuesday.
Next Tuesday, right after class.
Yep.
I have a question quickly about the extra credit. 5 question, I read it. You have to do and put it in a PDF and submit it, yes? The reason I'm willing to do it because in some assignment I got less points.
Yeah, do
So
it,
to
do it.
cover that.
Yeah, do it.
How many scored the extra credit?
10 points.
10 points.
So assignment is like 7.5 points. A little bit more than one assignment.
Wow, that's good because it
Yeah.
raised up my, and also the extra credit, I love it. It's shaking you when you're writing, reading, you're doing something, you learn.
Yeah,
That's
there you
it.
go.
Thank
The
you
extra
for-
credit, you can only do it once, or is it every?
There's one, and I forgot to tell everybody, but it's on the modules.
Okay.
Yeah, do the periodic table extra credit, then there's one for another unit, then there's one at the end.
Okay.
So there's 3 options for it.
She asked me that you extended that extra credit 1 day more or no?
Sure. Sure. I know. So let's do,
Oh, has the deadline, the extra credit?
just like everything, it's okay. I mean, it's gonna benefit you more if you do it now than later, but, so if we have, let's say we have 3 kilograms and we wanna know how many, centigrams this is. Okay, so we're gonna take 3 kilograms. And we don't want kilograms, so we're gonna convert kilograms into what?
Centigrams?
Into grams, good.
Oh, grams.
Oh, yeah, not centigrams, but grams.
Okay.
Because we're gonna go from kilogram, because this tells us how many grams it is. This tells us how many grams it is, right? That's why we go to grams. We go to the base always, okay? So we know that 1 kilogram is the same as 1,000 grams.
Okay.
Kilo means 1,000. So that goes away. Now we don't want grams, we want centigrams. So let's see. 0.01 grams is the same as 1 centigram.
I tried to look for it, but I couldn't find it.
Or we could do centi means 100, right?
Okay.
And how many 100ths do we need to make one? 100 of them. 100 100ths make one.
Okay.
Both ways work the same. I don't know which way you like to do it.
Okay. No, that makes more sense. Okay. Okay.
So grams goes away, we're left with centigrams. So we take 3, we multiply 1,000, multiply 100, and that's it.
Okay.
Does that make sense?
Yes, that did help a lot. Thank you so much.
Yeah,